Welcome back. Yesterday we discussed about splitting pattern and we worked out how many peaks we get when one spin is coupled to n chemically equivalent spins. Okay. By family tree approach, when one is coupled to n other protons, we wanted to find out totally how many peaks we expect at the chemical sheet of each proton and also total lines you can expect in the spectrum. So we took the example of weakly coupled spin system like 2 spin, 3 spin, 4 spin and showed how many peaks you expect. But remember those example you should never forget that I took the example of them where all these things are weakly coupled spin system. This type of intensity pattern everything you cannot work out so easily, family tree approach everything and the spin systems are strongly coupled. It is not possible. But I am just for making you understand in the most realistic situation, weakly coupled spin system when it is there, most often you come across that. First order analysis is possible. Easily looking at the spectrum you can analyze and this is the way you understand the multiplicity pattern. That's what I was telling you. Now, we'll go further today. I will introduce one more term called active and passive couplings. Very interesting thing. What is an active coupling and what is a passive coupling? You look at this my thing example like this. Again, I took example of 5 protons which are coupled among themselves. This is a coupled spin system. Remember I told you about the coupled spin system in one of the classes. When one proton is coupled to remaining other protons of different coupling strengths, it forms a coupled spin system. No matter one of the coupling maybe is very small 0, but it should be a part of the coupled spin system. Now in the coupled spin system, we come across situations. I want to tell you what is active coupling and what is passive coupling. Look at this one. Now I am going to look at the proton 1. That is, there are 5 protons. This is the chemical sheet of 1, 2, 3, 4, 5. 5 different groups of peaks are there. 5 different chemical shifts in the NMR spectrum, proton NMR spectrum. 5 different peaks are there. And each of them are coupled and pattern is different. Like we saw, AMX and 4 spin coupled. We have a different pattern depending upon the strength. Although number of peaks are same, pattern may be different depending on the coupling strengths. And intensity will be all same. That's what I said. Now, let us extend the logic. I am going to consider proton 1. I will detect this one. That means I am at the chemical sheet of proton 1. Let us say proton 1 is here. This is coupled to proton 2. What is its coupling strength? J12 because I don't know what is the value, but it is coupled to proton 2. It is J12. It is also coupled to proton 3. It is J13. It is also coupled to photon 4, J14. And it need not couple to J15. Does not matter. But these are all called active couplings. These are all when I look at the spectrum at the chemical sheet of this proton 1, I see although all are coupled spin system, only this is coupled to these 3. Because of this will be a doublet, doublet of a doublet, and doublet of doublet of a doublet. So it will get 8 lanes at the chemical shift of this proton. And from the 8 lanes, you measure this coupling, and this coupling you can get. It is easy to measure coupling strengths at the chemical shift of proton 1 by seeing the multiplicity of 8 lines. And that is called active coupling. The coupling that you are measuring at the chemical shift of a proton which you are observing, they are called active coupling. Remember, active coupling is the one where you are going to see the interaction strength. You can measure it at that particular chemical shift. Now, this coupling is 0, no problem. These couplings gives us the multiplicity for proton 1. So, active coupling gives you multiplicity at the site of this one. Now another thing, we will extend the logic. What about this coupling 2,5? What about 3,5? It has coupling strength of 3,5. What about 2, 3? What about 3, 4? What about 4, 5? What about 3, 4? I'm sorry, 2, 4. These are also there, coupling. Not that they in a coupled spin system, when you observe this, you observe multiplicity because of other protons coupling. But these were not absent, they were present. But you don't see it here. Okay? You don't see it at the proton chemical shift of site of 1. These are called passive couplings. Passive couplings are not seen when you detect the proton of a particular spin, which is an active spin. In which case, we call this as the active spin, and these are all called passive couplings. And the couplings which I showed in the previous case, these are called active couplings. This is an active spin. These are active couplings which are seen at the chemical shift of proton 1. And these are all passive couplings which are not seen at the chemical shift of proton 1. You understand the logic? What is an active spin and what is passive spin? This is an active spin, and all the protons which are coupled to this are active spin when I am observing this. When I look at the chemical shift of this one, all other couplings to other protons are active couplings. But all the coupling to other protons, then when I am observing this is active spin, and these are all passive spins. So coupling among the passive spins are called passive couplings. These passive couplings are not seen at the site of the active spin. Very interesting point. Must remember, this is very useful in understanding and analyzing the NMR spectrum later. Okay. Now, I'll ask a question. Now, I am going to observe proton 3. Now, when I am observing proton 3, which is an active spin? Active spin is proton 3. What are the passive spins? 2, 1, 4 and 5. These are all passive spins. And this is my active spin. Now, what if I am looking at the chemical shift of this proton in the spectrum? What are the couplings we are going to see? Coupling of passive spins with the active spin. That's what you are going to see here. Like what I said for the earlier proton. Now for this one, when this is active spin, you always see coupling between active and passive spins at the site of active spin. Now I see this coupling, I see this coupling, I see this coupling, I can see this coupling. So when I go to the chemical shift of proton 3, I'll see coupling. Because of this, it will be a doublet, doublet of a doublet, doublet of a doublet in D. So it is further split. So when I see this and analyze the multiplicity at this proton, at this chemical shift, I get 3 coupling strengths. So this is an active spin, these are passive spins. So when you are observing a proton, you always measure coupling between active and passive spins. And you don't get the coupling between passive spins. These things you will not see at this site. Remember this. These couplings are called passive coupling. You will not see at this. You understood? I give you 2 examples between active spins and passive spins. I hope you would have understood something now. At some point you would have got, right? So, and this will not get reflected at the chemical shift of the proton 3. Let us take a realistic example. Active and passive couplings in homonuclear coupled spin system. I'll take an example of a molecule like this. A hypothetical molecule, 3 spins coupled. Forget about this A3COO group. This is not coupled to any of these things. That is this thing. So we will not worry about this. We worry only the chemical shift of H, M and A. Only 3 protons, that 3 chemical shifts, let us worry. Let us the spectrum is taken. Proton spectrum. We get this is the proton spectrum. What is the logic? When 3 protons are coupled, you know, see, first thing you should have, look at the spectrum. All are of equal intensity. When 3 protons are coupled, use my formula. When A is coupled to M and X, there are 2 other protons which is coupled to 2 to the power of 4. That is 2 to the power of 3 minus 1. That is 2 to the power of 2 2 square, and each chemical sheet of A, you get 4 peaks because of coupling to this. At the chemical sheet of M, you get 4 peaks because of coupling to A and X. At the chemical sheet of X, you get coupling to AX and MX, and you get 4 peaks. See, always you get 4 peaks of equal intensity. This is a weakly coupled AMX spin system. We worry about weakly coupling later, but this is the spectrum of equal intensity. As I was telling you always, although you get four lines, but the pattern is not same. Multiplicity pattern is different. Remember, this is larger spread here. This spread is dispersion is more than this one. This, see here, this spread is larger. This spread is small. So here this is larger than this, and this is smaller. Why? Because when I am expecting looking at A can have coupling to this and this, trans coupling and cis coupling of 3 bond. When I am looking at M can have a cis coupling to A and geminal coupling to X. When I am looking at X can have a geminal coupling to M and trans coupling to A. So all are of different strengths. As a consequence, this multiplicity pattern is not identical for all the 3 protons. That's a plus point. Please understand this important point now. They are not identical, they are all different. As a consequence, this is the spectrum. Now let us analyze it and get always all the couplings information from this. Now we can understand what is active and passive coupling by analyzing the spectrum. Let us concentrate this region. What is this region? This corresponds to proton A. So proton A, center of this multiplicity pattern gives you chemical shift of A. That I have been telling you. Don't get confused. Now the 4 peaks are there. When this I am observing, what is my active spin? When I am observing this proton, remember, this is the active spin. Proton A is active spin. So now what are the passive spins? X and M are passive spins. It means, remember I said, at the site of the active spin, you always get coupling between active and passive spins. So at the site of A, I get coupling between active and passive spins. So I get a coupling between this spin and this passive spin, this active spin and this passive spin. So at the site of A, which is active spin, I get AS coupling and AM coupling. They are passive couplings. Very interesting, right? So what about MS coupling? That is the coupling between passive spins. I told you, coupling between passive spins are not reflected at the site of the active spin. You always get coupling between active and passive spins and not coupling between passive spins at the site of active spin. This is a very, very important statement. Please remember, you need it to analyze the spectrum very often. Okay. We'll go further now. This is an active spin and active couplings are AM and MX, passive coupling MX, and what is going to happen is this I will consider as a large coupling, AM coupling. No, this should be AX coupling, doesn't matter. Trans is large, it doesn't matter. This is one coupling and this is other coupling. Oh, this is large still, okay. This is a small coupling. It should be other way. This is AX and this is AM. Because this AM vicinal 3-bond coupling is smaller than trans coupling. That is in realistic situation. But okay, let us assume whatever may be the case. This is the way you understand. This large coupling is one of them, and this separation gives me small coupling. So at the site of this, I get AX coupling and AM coupling, which are active coupling between active and passive spin. These are called active couplings. Coupling between active and passive spins are called active coupling, and passive coupling is coupling between passive spins. So I don't see MX here. Go further. At the chemical shift of M, what is the active spin? M is the active spin. So what are the couplings you see at this site? Coupling between active and passive spins. So these two are the passive spins. So I get J AM coupling, J MX coupling here. What about J AS coupling? That is passive. You don't see that. See, in this case, Active couplings are AM and MX, you will see, and passive coupling is AX, you will not get here. Now go to the chemical sheet of, okay, this is some way we can interpret. Now go to the chemical sheet of X. What are you going to see in the X? X is the active spin. What are the passive spins? M and A. So what are the couplings you see here? Coupling between MX and AX. They are active coupling. What is coupling? AM. It's a passive coupling. So because you are observing X. So this you will not see. So active couplings are AX and A and MX, and AM coupling is passive and you don't see it. You understand how the spectrum influences active and passive coupling influences the spectrum. If you have a 3 spin system like this, just by looking at the pattern of the spectrum, you can start analyzing, always keeping in mind when your particular chemical sheet of the particular proton you are looking at is an active spin, remaining are passive, and at this side you always get coupling between active and passive spins. No coupling is seen between passive spins. With that point, you can analyze any spectrum given like this. Get the point? This is what it is. You can analyze everything here. All this coupling can be measured very easily. Okay. Now we can go to a active and passive couplings. This was an example I took for homonuclear 3 coupled spin system. Okay. Homonuclear 3 coupled spin system is different. Now what happens if I take a heteronuclear coupled spin system? Which are active and which are passive? Because in your realistic molecule, you can have different nuclei NMR active spins present. There will be a coupling among all the spins. Remember I said NMR in the spectrum does not distinguish between active and passive spins. Coupling will be there. I mean, whether it does not distinguish between homo and heteronuclear spins, all coupling can be present in the spectrum. But you have to analyze. Let us see what happens in a heteronuclear coupled spin system. I take example of 13C labeled dibromofluoromethane. This is the molecular structure. 13C labeled. Labeled means in your you should understand in chemistry, I am enriching that carbon 13. Instead of 1% abundance, I will now make it 100% by doing some chemistry. Then what happens? This is also an abundant spin. So I can see the coupling of this to others easily. If it is natural abundant, 1% abundant, then normally we don't see the coupling. We see, but we don't worry about it because they are satellites. We worry only about the ketone labeled isotope. Because satellite analysis we do unless it is important, we don't bother about it. So now in this system, 3 coupled, this carbon 13 is labeled. As a consequence, we get there are 3 different heteronuclei here: proton, fluorine, and carbon, which is also labeled. So 3 active spins are there. All are 100% now, abundance. I showed in one of my earlier classes, proton and fluorine are highly abundant spins and with large gyromagnetic ratio, more or less comparable. And this also now made abundant, but gyromagnetic ratio is not in my hands. I cannot change. I can make the abundance larger, but I cannot control the gyromagnetic ratio. So it doesn't matter. Now, as far as I am concerned, all the 3 are 100% abundant now after labeling. You will look at the NMR spectrum. Now, without showing the spectrum, I will ask you a question. If I look at the proton spectrum, what do I get? In one spectrum, you cannot see this nuclei and this nuclei, right? Because they are all different nuclei. If I have to see a fluorine, I have to go to fluorine resonance. If I have to see the carbon spectrum, I have to go to carbon 13 resonance. If I see the proton spectrum, I go to proton resonance. Now, we'll see this is a, remember when they are weak heteronuclear spin system, they are weakly coupled because the chemical shift separation is quite large. This is in megahertz. This is, let's say, 500 megahertz. This is 470 megahertz. This is 125 megahertz. See, Zeeman splitting, if you consider Zeeman interaction, they are separated by several megahertz away. Or in other words, you say the chemical shift separation is megahertz away. It's larger chemical shift separation. They are all resonating at different resonating frequencies separated by megahertz. So it's a weakly coupled spin system. You understand? All heteronuclear spin systems are weakly coupled because of large chemical shift separation. Now look at the proton spectrum. Very interesting. Now I'm looking at the proton spectrum, which is the active spin. All of you must understand. In the case of this one, when proton is if I am looking at the proton spectrum, this is the active spin. Then what are my passive spins? Both fluorine and carbon are my passive spins. So what couplings I see at the proton? Coupling between proton and fluorine, JHF. Coupling between proton and carbon, JHC. Only these two couplings are seen in the proton spectrum. See, proton is active, 19F and carbon 13R. Passive spins, I get JCH and JFH in the proton spectrum. JCF I don't see at all. I cannot extract from the proton spectrum because this is the coupling between passive spins. I do not see. Now go to the fluorine spectrum. The fluorine spectrum, which is the active spin? Fluorine. Which are the passive spins? Proton and carbon. Now, when F is active spin, proton and carbon are passive spins. What I am seeing here, in the fluorine spectrum, I see JHF and JCF. These are the active spins, active couplings. What about JCH? I am observing this. These are passive spins. This coupling between passive spins are not seen. Now go to the next example. 13C is active spin. Which are the passive spins? Fluorine and proton are passive spins. So what are you going to get in the 13C spectrum? Fluorine carbon coupling and proton carbon coupling. What about FH coupling? No, these two are passive spins and coupling between passive spin is not seen. So you get only JCH and JCF. JHF is absent. Understood? A simple example I took, 3-spin system, to show you what are active and passive couplings, what can you detect when you detect the active spin, and you always remember very important points. Whenever I am seeing the spectrum of a coupled spin system, all may be coupled, with some coupling may be zero, no problem. Go to the chemical sheet of a particular spin or a particular nucleus in a molecule, whether it is homonuclear, heteronuclear, doesn't matter. When you are observing that spin, that is an active spin. When you are at that chemical shift, when you are measuring the chemical shift and coupling at that place, analyzing that multiplicity, it is an active spin, and you get at that place coupling between active and passive spins. Go to other proton, that is the active spin, remaining are passive. There you get the coupling between active and passive spin and coupling of the chemical of the active spin. No passive couplings will be seen. Like that, this point, if you remember, very easily you can analyze lot of spectra. Okay. I hope you are catching my point of active and passive couplings. I introduced you the spin active and passive couplings and took the example of 3 protons and 3 heteronuclei, and I showed you what is an active spin, what is a passive spin, what is the active coupling between active and passive spin, that's what you see, and what are the coupling between passive spin which you don't see at the active state. This is a basic point you remember. And don't forget, because these are all very important as you go ahead further. Now I want to tell you something about what is called sign of the couplings. So, remember, when I was discussing you about the signs of scalar couplings, salient features of the coupling, I did mention to you the scalar coupling can be positive, it can be negative, or the value can be 0. When you measure this, for example, you go back here, you measure the separation. This is a coupling. I say it is 20 hertz. But what is 20? 20 is a number. Is it plus 20 or minus 20? That question can be asked. Right. So, scalar coupling can be positive or negative. It's possible. Then how do you know whether this separation is 10 hertz is positive or negative, or this separation to 100 hertz is positive or negative? We don't know. So let us understand what are the signs of the scalar coupling. This is a point you must understand. Especially in lot of examples I have seen when people report coupling between fluorine and carbon, one band coupling, JCF, which is usually larger of the order of 300 hertz. They write JCF 300 hertz. It is wrong because JCF one bond is always negative. You should report as minus 300, not just 300, because this coupling is negative. It is known. So that is why sign of the coupling sometimes is very important to mention. In fact, without knowing the sign of the coupling, sometimes in the application of biological studies, it's very difficult. When you want to get some residual coupling, I'll explain to you later when we go further. First, understand this one. What is sign of the coupling now, and how it is used later. I consider this Dirac model. We discussed this. So what is when we introduce the coupling constant? I said that the most stable orientation of magnetic moments of proton and electron are one, they are anti-parallel to each other. Very first slide when I introduced scalar coupling, I said mechanism of coupling. I was telling you when one of the magnetic moment of proton I took, which is parallel to the field, when this is like this, electron has to be opposite for the stable configuration. But because electron has a negative magnetic moment, I wrote both are parallel. Then I said, according to the Pauli principle, this electron and this electron are paired, and as a consequence of this electron is down, this proton has to be up. Or this is as good as telling because they are opposite to electronegative, magnetic moment of electron is negative. Again, you don't have to write it up, it is like this. Now look at this thing. Since electrons are negative, I wrote like this. Finally, the magnetic moment of protons, when it goes through covalent bond, it ensures by this is a Fermi interaction. I said this is because of the Pauli's principle. This model again is called a Dirac model totally in a classical way, in a simple way of explaining the coupling interaction. When this is parallel, it forces the carbon, one bond which is there, coupled with a sigma bond, single bond, opposite to this orientation. You understand? Because of this Fermi contact and Pauling principle, where these two get paired, and because these two again Fermi interaction, this proton orientation, this magnetic moment, which is parallel to the magnetic field, forces this carbon to be orienting opposite to that, and this is called lower energy configuration. It is when both the spins are anti-parallel to each other, nuclear spins, it is lower energy. Lower energy is a stable configuration. Okay, correspond to J is positive. 1JCH is always positive. The low energy configuration, is stable configuration, and when these two are anti-parallel, the convention is when the two coupled spins have opposite orientation like this, the coupling is positive. Very easily you can work out. But now one bond JCF if you take, I said one bond JCF is negative. You can work out, go back, and if there is a difference, we will see why it is. Okay, the lower energy when both nuclear spins are anti-parallel corresponds to J is equal to greater than 0. That is why if you go back and see in the literature, 1JCH is always positive. 1JCH is always positive because orientation of this proton spin and carbon spins in one bond, they are always opposite. You can work out by this simple Dirac model. Now let us go for 2 bond sign of JCH and 3 bond sign of JCH. I'm considering only proton carbon. Now, up to this we understood this proton forces this to orient opposite to this. Now continue further. Because of this is orienting like this, and as a consequence, this forces to orient like this. You understand the problem? What is happening? One band, this force this to be orienting anti-parallel to this. Continue the same logic here. Again, bring in the Pauli pairing. Afterwards, and see that this carbon is forced to orient in the same direction as this one. When you go through two chemical bonds, proton orientation and the carbon which is two bonds away, the carbon spin, both orient in the same direction in the magnetic field. What did I say in the previous case? When they orient anti-parallel to each other, it is lower energy state, you see. Lower energy state when they are anti-parallel correspond to the positive J coupling. Please understand that's a convention now. In this case, what is happening? They are parallel to each other. It is higher energy state. Little unstable configuration. This has a higher energy state. As a consequence, we say 2 bond JCH is negative. You understand how we get the sign of the coupling? Just by using, here we use the Fermi contact interaction, here to here Pauling interaction, again Fermi contact, here to here Pauli pairing, again here Fermi contact. Went by the simple Dirac model, and we found out 2 bond JCH is negative. You are all with me, I hope. Now, let us continue further. What happens if I get 3 bond coupling? Up to this you have understood. Simply add one more bond. Now how does it orient? Remember, same way, now this is a parallel orientation with respect to this one. Electron orients in such a way it gets a stable configuration. Again, we say Pauli pairing, and this forces this to be opposite with respect to this. So that means when you consider 3 bond CH coupling, the orientation of the magnetic moment of this proton and the proton which is 3 bonds away, they are anti-parallel to each other. They are opposite to each other. They are not orienting in the same direction. What does it mean? This means this is a lower energy state. When it is a lower energy state, it means sorry. See, this is JCH. I wanted to change that. Okay, and this is a low energy state, and JCH. I'm sorry, correct. HH was correct. 3 bond JHH. Okay, C to H. H to C, C to C, and then C to H. Okay, 3 bond JHH. This was correct. I should not have changed. Okay, 3 bond JHH is positive. On the other hand, there is a mistake in the sense I should make this a C, then CH. It makes it. Now I have corrected this slide. This is going by CC bond only. This is not proton, this is not CH. Go CC bond and then another H comes because I am looking at 3 bond JCH. 1, 2, and 3. So 3 bond JCH. Now it's a low energy state. Sorry, there was a mistake in the slide. I corrected now. This is correct. Low energy state 3 bond JCH is this proton and this carbon orients anti-parallel to each other. It is stable energy state, lower energy and stable configuration. Therefore, J3JCH is always positive. Okay, I hope you understood about the sign of the coupling. How to get the sign of the coupling. But next the question is, how does the sign of the coupling influence the spectrum? What happens if the J is positive? How does the spectrum look? If the J is negative, how does the spectrum look? Can I get the sign of the coupling just by looking at the spectrum? These are the questions which we have to answer now. You understand, in this class, I was briefing you about active and passive couplings. I took the example of 3 spins. I explained to you what is the active coupling, what is the active spin, what are active couplings. Active couplings are always coupling between active and passive spins. What are passive couplings? Coupling between the passive spin or among the passive spins. When you're looking at a particular chemical sheet of particular proton, that is an active spin. And you will always get the multiplicity at that side because of the active spin coupling to remaining passive spins. And no passive couplings will be seen here. This is logic. I showed the example for homonuclear case and 3 heteronuclear case also. And I introduced about the sign of the coupling. How the sign of the coupling can be can be observed depending upon the orientation of the magnetic moments of two different spins which are chemically bonded, especially CH, 2 bond, 3 bond we observed. And one is we observed 1 bond JCH is positive, 2 JCH is negative, and 3 JCH is positive based on the alignment of the magnetic moment of two coupled spins. If they are anti-parallel, it has different state. If they are parallel, different state. So depending upon it is a lower energy state or higher energy state. For example, when these two are anti-parallel, it is lower energy state. This and this are anti-parallel. Okay, and this, for example, this and this anti-parallel, lower energy state. This and this are parallel. It is higher energy state. Like this, we can start understanding about the sign of the coupling. I'll stop here. Next class, I will discuss about how the sign of the spectrum affect the spectrum. Okay, and then we start getting more information about other multiplicity pattern and analysis of the spectrum.